Hello there. So this is our continuation of section 2.1 from last time, and I just want to refresh your memories on what we did last time. We talked about what a derivative is, and it's essentially you take 2 points, you move them close together, and then find the slope between those 2 points. And we're going to do something very similar in the first part of our notes today. So our notes today there's kind of two parts to it. The first part is there's an alternate form of the definition to find a derivative. And then the second part is when are functions not differentiable? Like what would happen on a function such that you look at it and you say, I can't find the slope of a tangent line at that place. And so it's kind of two different halves to our lesson today. The first part is finding the alternate form for a derivative. And it's going to start very similar to what we did last time. Last time, we took a function, we took a point right here, and we named it. And for this point, I'm going to name it c comma f of c, which is what we did last time. C comma f of c. And I want to find the slope of the tangent line at c comma f of c. And then what we said was we take this second point, and move it as close as we can to the first point. But I'm going to name the second point a little different today. So last time we said, okay, let's move some delta x away from c. Well, this time, I'm just going to have the second point have its own x value. Okay, so last time we shifted some delta x away. This time, let's just call that x. Well, if the x coordinate of this point is x, then the y value is f of x. Okay, and what we want to do now is the same thing we did last time. I want to take the second point and move it as close as we can to the first point, and then find the slope between these 2 points, because that's going to be finding us the slope of the tangent line right here at c f of c. All right, so if I want to find the slope of the tangent line at c, we're going to take the slope between these 2 points, so it's going to be y2 minus y1, so f of x minus f of c, over x2 minus x1. Now last time, when we took that second point and moved it as close as we could to the first point, we said that delta x was getting close to 0, like that change in x was shrinking and shrinking and shrinking. Well, this time, there is no delta x, but what's going to happen is, as this point moves close to the first point, this x value is going to move closer and closer and closer to c. So this time, we want to take the limit as this x approaches this c value right here. And this is the alternate form for finding the derivative of a function at a location. It looks similar. It has some benefits and it has some disadvantages to it that we'll talk about. This form, I'll talk about the disadvantage right now. Well, let's talk about the advantage. This form removes a lot of the messy algebra that we did last class. If you remember how we had to plug like x plus delta x in for all the x's and then square quantities and all that, we had a lot of upfront algebra. This form removes all of that. If you notice, we're never plugging in quantities to our function. So it is very nice in that regard. The downside is this form will only find derivative values at locations. The other form that we did, you were able to find the actual derivative, like in terms of x, and then plug, several different points into the derivative and get those slopes out right away. This won't do that for you. This will only find the slope of a tangent line at one particular location, not in terms of x. Okay? So it has some upside, it has some downside. Let's use it and see how it gets used. So example 1, find the slope of f of this function at 4, 3 by using the alternate form. So I want to use this form right here. I want to find the slope of the tangent line to this function at 4, 3. So that means I want to find f prime of, in this case, 4. The slope of the tangent line at 4. So we just look at how the formula gets used. So now anywhere you see the c, we're going to put a 4 instead. So it's the limit as x approaches 4. So basically the second x value is approaching the first x value of f of x minus f of 4 over x minus 4. So anywhere we see the C, we put a 4. And now, just like the other times, we just have to do this formula here. We got to do the work. So we have the limit as x approaches 4 of the function, so x squared minus 6x plus 11, and then minus f of 4, which they tell you right here, it's the y value there, so minus 3 over x minus 4. We can combine the 11 minus 3, so we have the limit as x approaches 4 of x squared minus 6x plus 8 over x minus 4. Oops. And so here's a case now where you would try direct substitution. But the problem is, if we plug 4 in for the x here and x here, we're going to get 16 minus 24 is negative 8 plus 8 is 0 over 0. We get 0 over 0. But that doesn't mean the limit doesn't exist. That just means we have to try other things. And so if you notice, we can factor the top here. That becomes x minus 2, x minus 4. The x minus 4s go away. And now we can do direct substitution. Now I'll plug 4 in for x. 4 minus 2 is 2. So what that means is if we would graph this function, this parabola, and plot this point, the slope of the tangent line would be 2. So notice we didn't have all that upfront algebra of squaring x plus delta x and all that sloppiness. But again, the downside is this won't find the actual derivative function, just the slope at a point. That's what this will find you. Example 2. Find the slope of g at 1, negative 2. All right, so let's do it. So we're looking for g prime of 1, slope of the tangent line at 1. So we're going to take the limit as x approaches 1 of g of x, so this first function, 3x to the 5th plus 2x minus 7, so that's g of x, and then minus g of 1, so minus negative 2, so plus 2. So it's g of x minus g of 1. That's what this is. Over x minus 1. Probably should have wrote out the formula again, like I did in the previous problem. My bad. Okay, let's combine like terms. So we have the limit as x approaches 1 of 3x to the 5th plus 2x minus 5 over x minus 1. Or we could try direct substitution, plug 1 in for all those x's, but we would get 0 over 0, so indeterminate form, can't do it. Okay, well, like the last problem, we would look to factor. So let's think about how we can factor quintic polynomials. Quintic polynomials. Well, we've never learned that, and you're not going to, because I don't know how to factor a quintic polynomial. So we're stuck at this point. Except we are not. What we need to do, and this is why I love this class, just because skills that you've learned in the past just pop up time and time and time again. Back in Algebra 2, and I imagine in pre-calculus, you guys learned how to divide polynomials. We can look to divide these two polynomials and see if we get something better and easier to work with. And you had two ways to divide polynomials. There was long division, and then there was synthetic division. Now we're allowed to use synthetic division on this one because we're dividing by x minus 1. So I'm going to refresh your memories on synthetic division. And there's no way around this problem other than to do this. And it is something that sometimes just pops up. So synthetic division. We do our upside down bar. The thing that we're dividing by, whatever makes it 0, goes on the outside. So positive 1. We put all of our coefficients of the numerator in the top row here. Remember, any missing term, we have to put zeros in. So we have a 3. There's no x to the 4th, so we put a 0. There's no x cubed, so 0. There's no x squared, so 0. And then 2 minus 5. So that's the setup. And now we go through our process. That first number you just bring down. And then we multiply 1 and 3 together. That goes here under the 0, so 3. And we add straight down. And then we repeat. 1 times 3 is 3, add. 1 times 3 is 3, add. 1 times 3 is 3, add. 1 times 5 is 5. We get a remainder of 0. Now let's talk about why this was beneficial. So we had this fraction right here, and when we divide it out, we end up with this new polynomial, which actually turns out really nicely because there's no remainder. Remember, we started with an x to the 5th, and we're dividing by x to the 1st. So what's left, these are the coefficients of our new x to the 4th polynomial. Like this is 3x to the 4th plus 3x cubed plus 3x squared plus 3x plus 5. Like that's our new polynomial. That is what we can replace this whole fraction with. So we don't have any more fractions to deal with. Now I'm not saying synthetic division is something that, oh, you're going to see this all over the place. I don't know if I've done an AP practice problem where this showed up, but they have told us that it is a method for evaluating limits that students need to know. So it is something that could pop up. So we have the limit as x approaches 1, but instead of this fraction, we now just have this polynomial. 3x to the 4th plus 3x cubed plus 3x squared plus 3x plus 5. So we're taking the limit of that whole function as x approaches 1, and now we can do direct substitution. Now we could plug 1 in for all those x's. So when we do that, we just get 3 plus 3 plus 3 plus 3 plus 5. So 12 plus 5 is 17. That means if we would graph this function and plot the point on it at 1, -2, and draw the tangent line, it would have a slope of 17, which is very, very, very steep slope. There you go. Sometimes you just got to do synthetic division when factoring doesn't work out. 3. Same type of thing. Find the rate of change of f equals x squared minus 3 at 2, 1. So we're just going to do it again. So we're looking for f prime of 2. So it's the limit as x approaches 2 of f of x minus f of 2. So minus 1 over x minus 2. F of x minus f of 2 over x minus 2. And then we just see if things simplify. So x squared minus 4 over x minus 2. Here we don't have to do our division because we can factor. We can factor x squared minus 4. X plus 2, x minus 2. X minus 2's go away. And then we could retry direct substitution. Plug 2 in. 2 plus 2 is 4. 2 plus 2 is 4. There you go. So it is rather nice, if you look through, aside from the synthetic division, the setup is very, very nice. You're not plugging in quantities, you're not squaring binomials or any of that stuff. But again, the downside is this will not calculate the derivative of a function for you in terms of x. So if they would say, find the rate of change of this function and then gave 10 different points, we'd probably want to find the actual derivative and then plug those points into it rather than doing this 10 different times. So it has its advantage and disadvantage, but that's the alternate form for finding the derivative of a function at a certain location. The second part of the notes is, what if you had a graph and you couldn't find a derivative at that place? Like you couldn't find the slope of a tangent line at a certain location. So when are functions not differentiable? And I just have a few examples that we're going to kind of discover. I could just tell you. I could easily just tell you. But I'm going to show you kind of the why, the breakdowns and what happens and why we can't use our normal rules here. So if I want to find f prime of -5 for this function, well, let's go through our normal setup. If I want to find f prime of -5, well, we would take the limit as x approaches -5 of f of x minus f of -5 over x minus -5, so x plus 5. Okay. And now let's go ahead and do this limit. Let's plug in our stuff. We're going to take the limit as x approaches -5 of the original function, so x squared minus 25 over x plus 5, that's f of x, minus, let's find f of -5. So when we plug -5 in for f right here, when I plug -5 into this function, let's see what we get. We'll get 25 minus 25 over -5 plus 5. We get 0 over 0. Now you could say, well, that means we got to factor and cancel. Well, if you remember a couple classes ago, when you factor and cancel, you're creating a new function. When this question says find f of -5, I want to know the value I get on f when I plug -5 in for the x's. And you don't get a value. Think about what's happening at -5. Your first instinct is to say, oh, there's a vertical asymptote. There's not, because if you factored, the x plus 5's cancel. So there's actually a hole at -5. Regardless, there's a discontinuity, and so there's a hole there. We can't find the value. I don't know what this is. And that just means the rest of the problem breaks down. We can't find this limit. There's nothing we can do. And so what we say is f of x, this original function, is not differentiable at x equals -5. When we went through this limit process, it's impossible to get a value out because there is no f of -5. So we say f of x is not differentiable at x equals -5. But then the question is, well, why? Why isn't it? Well, it's because this function is not continuous at -5. There's a hole, but in general, it's not continuous. Anywhere a function is not continuous, then that function is not differentiable at that location. So you have to be able you have to have continuity to have a chance at being differentiable. Okay, so that's the first thing. So the initial question says, when are functions not differentiable? There's going to be 3 cases. This is the first case. If a function's not continuous at that x value, it's not differentiable. You can't find a derivative value there. Okay. The next situation. All right, so now I have the absolute value of x plus 3. It says graph it, but we should have an idea what this graph looks like. The regular absolute value of x function is that v shape, when you have that v, and then this is just shifting it left 3 units. So we're going to have this. So that's the graph of g of x. Okay. Now what I want to find is g prime of -3. Okay, I want to find the slope of the tangent line right here. So I'm going to go through the process. G prime of -3 equals the limit as x approaches -3 of g of x minus g of -3 over x plus 3. So I'm just setting up my limit work. And let's plug our stuff in. So we're going to take the limit as x approaches -3 of g of x, which is the absolute value of x plus 3, minus g of -3. Well, in the last problem, when we tried to find f of -5, we didn't have a value there. Well, here we do. If I plug -3 in for this function, we get 0. So we can do that. So minus 0. I'm just not going to write it because we're just subtracting 0. Over x plus 3. Okay. So now, whatever the answer to this limit question is, that's the slope of the tangent line at -3 to this function. Well, let's think about how we analyze this limit. This should look familiar to you guys because I've asked this question of you guys like 5 different times. Think about how we find limits. We can't just cross these out. There's no factoring and canceling. But if you remember that graph that we've done several times, like if I try to analyze this limit graphically, remember at -3, anything to the right of it is going to be +1. And then anything to the left of it is going to be -1. We've seen this graph show up time and time again. What that means is this limit does not exist. There is no value because from the left and from the right, we don't approach the same number. This limit does not exist. Since this limit doesn't exist, then if we go all the way back here, that means g prime of negative 3 doesn't exist. That means there is no value here. That means that g is not differentiable at negative 3 because this value doesn't exist. So we'll talk about why here in a second, but we say g of x is not differentiable at x equals negative 3. Let's think about why. Think about what's happening at x equals negative 3. There's a lot of different words that teachers use to describe it, but I like to use sharp corner. There's like a sharp turn right here. There's an abrupt turn. So as you're going this way, it goes, and then changes direction immediately. And so anywhere there's a sharp corner or a sharp turn, your function's not going to be differentiable. So if we said why? Because there's a sharp corner. So anywhere you have a function where there's some abrupt turn, then the function's not going to be differentiable at that location. And the reason is, I'll get into this a little bit more. If you think about a parabola, when we're looking for slope of a tangent line, what we're really looking for is, let's say I wanted to find the slope of the tangent line right here, okay? We still look at from the left and right. We don't talk about this a lot, but if I draw tangent lines, leading up to that place, here, and I get here. If I do that from the left and the right, the tangent line that we end up getting is the same from the left and the right. So we could say it's differentiable there. With a sharp turn though, like if I draw my line here, and here, and here, and here, it never changes direction. The slope is approaching whatever this value is. And then from the right, it's approaching a different value. So that's why at that sharp turn, we just say the function is not differentiable there. All right. The last case, we have x to the 1/3 power. Okay, it says graph it. I will just show you the graph of x to the 1/3 power. It's similar to x cubed, except it's the, 180-degree rotation. Is that right? No, that wouldn't make sense. 180. It looks like this. Whatever. I'm actually really proud of my graph right there. It's really pretty. Really pretty. I love it. Okay. So I want to find h prime of 0. Okay, here's the graph right here. I want to find h prime of 0. Now, first of all, at 0, is this continuous? Yes, it is. We just go and we just draw the graph. Pencil never leaves the graph. This is continuous. Is there a sharp corner or a sharp turn here at 0? Well, no, it's nice and smooth. It's nice and smooth. There's no abrupt change. So it passes the first two conditions. Okay, well, let's go ahead and find h prime of 0 doing our whole limit stuff. So h prime of 0 equals the limit as x approaches 0 of h of x minus h of 0 over x minus 0. Okay, so we have the limit as x approaches 0 of x to the 1/3, because that's h, minus h of 0, so plug 0 in for h and we get 0, so minus 0, over x. And we can use our exponent rules to clean this up a little bit. Like if you do 1/3 minus 1, this is the same as x to the negative 2/3, but it's really the same as 1 over x to the 2/3. So think about now this function here. If I would plug 0 in, I get 1 over 0. What that means is this function has a vertical asymptote, and so this limit doesn't exist. That's what we're showing here. This limit does not exist because there's a vertical asymptote at 0. What that means is h prime of 0 does not exist. There's no value. What that means is that h of x is not differentiable. At x equals 0. We got to talk about y. What's happening at 0 that would cause the function to not be differentiable? Well, the reason I thought my graph is so pretty is because that y-axis, you could see exactly what's happening. You know, if you think about tangent lines, as you go from left to right, if you would keep drawing tangent lines, right here at 0, that tangent line gets vertical. At that one instantaneous moment, your tangent line is vertical. And if you think about slopes of tangent lines, or vertical lines, sorry, they're undefined. And so anywhere you have a vertical tangent line, then your function is not going to be differentiable at that location. So there's a vertical tangent line. So the slope is undefined. So those are the 3 times your functions will not be able to have a derivative value at a location. So I'll just put it up here instead of rewriting it all out, because I already had written this previously. So those 3 times are, if your function is not continuous at x equals c, so that could be a jump discontinuity, that could be a vertical asymptote, that could be a hole, but if your function is not continuous, it's not differentiable. If your function has a sharp corner or sharp turn at x equals c, it's not differentiable, so that's that abrupt change in direction. And then if there's a vertical tangent line at x equals c. All right, that's the end. Good luck on your assignment, and let me know if you guys have any questions. Peace.